Good morning. Um, so we just looked at the ideal gas law moments ago, and as useful as the ideal gas law is in describing the relationship between pressure, volume, and temperature, it doesn't give us any insight whatsoever as to what's going on the microscopic level with the particles themselves and their masses and their speeds. So I'd like to derive for you sort of an equation that will hopefully solidify your understanding of what temperature is truly in terms of those microscopic properties I just alluded to, the particles themselves, their mass, their speeds. In the 1800s, a physicist named James Clerk Maxwell actually worked calculations out for the distributions of the molecular speeds in an ideal gas. And up here I've drawn a figure that comes from your book for oxygen diatomic O2 at different temperatures. And so we've highlighted two curves, the 300 Kelvin curve, whose average speed in that collection of molecules at 300 Kelvin would be about 400 meters per second. And then the 1200 Kelvin curve, where the mean speed is around 800. I've graphed the number of molecules as a function of their speed. I bring this up just to point out that in a given sample of gas, there is a range of speeds. There's not a singular speed associated with an ideal gas. I need you to hearken back to a couple things you studied in your last physics course. First of all, we recall that speed is simply distance over time. And I want you also to remember that there's this property called momentum that particles possess. And momentum is the product of mass and velocity. I'd like you to consider a cubical box whose side length is L. L. And let's just consider the force exerted on an individual particle in this gas by the right wall of this cubical container. Now, let's assume for the moment that the molecule is moving to the right with a speed plus v, or velocity plus v, and a momentum plus mv, and that it collides with the wall and rebounds with not losing any kinetic energy, just changing its direction, with a momentum negative mv. So it hits with mv and it returns away from that wall with negative mv. And I want to remind you that this is what we call the impulse momentum theorem, but it's really just Newton's second law solved for this quantity force times time, which we call impulse, and the change in momentum on the other. If we divide it by delta t, you'd have F equals ma, right? In fact, here we are, F equals ma, where a is change in velocity over change in time. Now that's the force on the particle. Now, let's look at this. The change in momentum, m delta v, is the final negative mv minus the initial positive mv. And if you notice, the numerator here will become negative 2 mv when we sum these together. Now the time over which that change in momentum occurs is really, for that one particle, the total trip distance between collisions, which is 2L, divided by v. X over v is t, and the distance between collisions is 2L. So with that substitution, the change in momentum is negative 2mv divided by time, which is 2L over v. Simplifying that, the 2's cancel, and multiplying by the reciprocal, we get negative mv squared over L is the force on the particle from the wall. Now the force on the wall exerted by the particle is just the opposite of that. Newton's third law says for every force on an object, there's an equal and opposite force exerted by that object. So the force on the wall is positive mv squared over L. Now let's talk about the total force from some collection of particles. N, some capital N number of particles. Now the particles move in 3 dimensions. And so on average, only a third of them are going to strike that right wall. So the total force on that wall is n over 3, a third of the total number of particles, times this force on the wall, mv squared over L. Now I've put a bar over the V squared because, again, the gas possesses a Maxwell distribution of speeds. And only the average speed is relevant in terms of the average force generated by all these particles together. So we talk about this in terms of average speed. Now, there's something that can be oftentimes confusing for kids, but the square root of the average of the squares of all the speeds is something given the term RMS speed. And RMS stands for root mean squared speed. So the root of the mean of the squares. And we just define the square root of the average of all the speeds, of all the squared speeds, square rooted as the root mean squared speed. With that substitution, the total force becomes n over 3 mv root mean squared, the root mean squared speed squared over L. Let's go back to something that the ideal gas law does ask us to consider: pressure. We know pressure is force over area. So in this case, force divided by the square of L, the length of the side of each dimension of the cube. Let's go ahead and put in this for force and divide by area, which is L squared. And that becomes n over 3 mv squared, root mean squared, speed squared, over L to the third, right? Because when you divide by a fraction, multiply, that becomes cubed. And recognizing that L cubed is volume, and multiplying both sides by volume, we have PV, just multiply that out as volume, and we have PV equals n over 3 mv root mean squared squared. Now, I'm going to do a little trickery here and simply multiply this thing above my hands by 1. But I'm going to choose 1 in the form of 2 times a half. And what I mean by that is I'm going to multiply this by 2, so it becomes 2/3 n. And then I'm going to multiply the interior of the parentheses by 1/2. And that, of course, becomes 1/2 mv squared, with the root mean squared speed being the speed in question. I bet some of you saw this coming, because long ago when we saw mv squared, some people might have been saying, hey, that's something I know about. I've seen that before. That's related to kinetic energy. Indeed, this is the average kinetic energy of all the molecules in that sample of gas. That is the average kinetic energy of those molecules. So we can rewrite this as PV equals 2/3 n times the average kinetic energy, Ke bar. So to kind of bring us back to where we started with the ideal gas law, we have PV equals 2/3, a constant, times the number of particles in the sample, which if it's sealed is a constant, times the average kinetic energy. So the pressure and volume relate directly to the average kinetic energy. But we also know that PV equals nKT, the ideal gas law. And recognizing that the right-hand side of both of these expressions, the left-hand side is the same, P times V, I can just put 2/3 NKE equal to NKT. And recognizing that the N cancels, and multiplying by 3/2, we arrive at KE equals 3/2 KT. This is quite useful, really, because it tells us that we know that K is Boltzmann's constant, just the gas constant divided by Avogadro's number. So 3/2 K is just a constant. So what we have arrived at is an expression that says, hey, the temperature of a gas depends solely on the average kinetic energy of the particles that compose that gas. In other words, the average translational kinetic energy determines the temperature of a gas, no matter what the pressure and volume are.